Let's work on integrating in polar coordinates with example 18.2. Here, we're not going to integrate. We're just going to describe a region. So I want to give bounds to my iterative integral in polar coordinates. All right, let's look at the region R that lies inside the cardioid 1 plus cosine theta and outside of the circle r is equal to 1. So let's go ahead and draw this. Let's give our Cartesian plane right there. And I don't want to think about Cartesian coordinates. I guess I shouldn't have said Cartesian plane. This is a polar plane where all of our points can be described with a radius from the center and a theta, an angle away from the x-axis, the positive x-axis. So if I think about the cardioid, 1 plus cosine of theta, in this direction, when my theta is equal to 0, my cosine is equal to 1, so I have a value of 2. And then as I rotate around the plane, my cosine values here in this region are still positive, but when I hit the angle of pi over 2, my cosine value is 0, so I just get a 1 right there. So it's going to look something like that. And as I keep rotating, over here, my cosine values are negative. So when I add 1 to a negative value, it's going to get smaller. And then when I'm on my negative x-axis, that's when theta is equal to pi. So my cosine value is -1. So 1 plus -1 gives me a 0. Right, so this really isn't calculus 3. This is more trigonometry. But this is what a cardioid would look like. Or rather, this is what this cardioid looks like. All right, and I want to find the region R that lies inside of that cardioid, but outside of the unit circle. So I'm looking for this region here. So if I think about drawing vectors from the origin, right, vectors are a good way to think about this because vectors are polar coordinates. They're radiuses and angles. Then my iterative integral for theta is going to be between minus pi over 2 to pi over 2. So the outside integral, theta, is going to run from, let me do this in a different color. So minus pi over 2, and it's going to swing all the way up to positive pi over 2, right? Because I want to collect all of this area. So my angle is going to swing from all the way down here to all the way up there. Now my radius, think about this red vector right there. It enters your region of integration when r is equal to 1. So that's your minimal r value. And it exits your region of integration when r is equal to 1 plus cosine of theta, right? Because this curve right there is the cardioid 1 plus cosine of theta. Right, so the main idea here is draw the region and then draw a vector through that region, and then the angles that are on the outside and the inside are going to provide your bounds for the theta, and then the first r value will be the minimal r value, and then whenever you exit your region, that's going to be the biggest r value right there. But as always with integral problems, draw the picture and it should give you an idea of what to do. So what do we think? Give the limits of integration for integrating a general function. So I don't know what function this is. But I know that I integrate with respect to theta last, I integrate with respect to r, that's this inside integral, and I have to remember that whenever I integrate in polar coordinates, that the measure of the space has an extra r out there.